So today's webinar is on a geophysical response in lithium brine monitoring, new exploration paradigms, and sustainable green lithium. So this webinar is organized by SEG, Europe Regional Advisory Committee, and we thank SEG for organizing it, of course, as well.
Thank you, Anna, for volunteering to give this presentation. As Eamon stated, your title is Geophysical Response in Lithium Brine Monitoring, New Exploration Paradigms, and Sustainable Green Lithium. Anna is simultaneously earned her degree in physics from the Faculty of Exact and Natural Sciences, Engineering, and Master's in Geophysical Engineering from the Faculty of Engineering, and a PhD summa cum laude at Buenos Aires University. And as if that wasn't enough, she is an oil and gas production specialist. She is a current member of the SEG board. She was previously the chair of the SEG Latin America Regional Advisory Committee, and she was also a district representative on the SEG Council. So thank you very much, Anna. You're fluent in many languages, thankfully. So welcome, and thank you for volunteering for the Europe Regional Advisory Committee course. Thank you.
Thanks to you, Laurie, and good morning, everyone. And thanks to the European Regional Advisory Committee for the invitation to talk about this hot topic. And today I'm going to talk about the geophysical response in lithium brines monitoring. I will talk about some new exploration paradigms and provide a brief introduction to sustainable green lithium. See, this is the talk is organized in this way. First, I talk about the objectives and some general remarks of the lithium deposits. Then I'll move to the analysis of the geophysical responses in salt flats. Then I'll talk about the effective multiphysics toolkit and the validation of that toolkit. Then I will introduce to the sustainable green lithium, then move to the conclusions and sum up. So as you know, the energy transition drives the energy sector to renewable energies and electrification, being the critical minerals key players in the industrial development map. The critical minerals comprise rare earth elements and 35 other elements, including lithium. And the criticality of the lithium, among other reasons, is due to the fact that 65% of the global resources are located in the so-called lithium triangle, located in Argentina, Bolivia, and Chile in South America. Regarding the geophysical problem, the lithium problem is considered a complex problem because it has very low electrical resistivities, variations in salt concentrations, low contrast of acoustic impedances, and also the hydrogeological system is very dynamic. And from the operational point of view, the problem also is complex because we are at high altitude or 4,000 meters height. The soil has a strong mechanical instability, which makes the survey acquisition very complex. So the objective of this talk is to discuss about different geophysical responses in different salt flats, then to present a suitable combination of geophysical techniques that fit the current lithium exploration objectives, then to validate this methodology, and finally introduce to the sustainable green lithium. Well, let's move to some general remarks. And first, I want to talk about the different lithium deposits. We have different type of deposit. The most famous to date are the continental brines, or the so-called closed basin brine, which holds 60% of the global resources. Then the pegmatites, or hard rock or hard mining, which holds about 30% of the global resources. We can obtain lithium from oilfield brines, from lithium clays and lithium zeolites, and also we can obtain lithium from geothermal brines. In the bottom left, we can see a scheme that shows the different sources or different lithium deposits, and also it is shown the range of concentrations. And this explains why today the salt flats are very important in the lithium global map, because we can find concentrations of almost 4,000 ppm per million of lithium. Of course, we can find lithium also in the ocean, but if you can see that we have very, very low concentrations. If we move to pegmatites, we can see that we can have a good range of lithium concentration from 300 to 4,000 ppm. And in the bottom right, we can see the main producers of lithium today. As I told you, South America holds the 65% of the global lithium resources. So Bolivia, Argentina, Chile, China, and the US are the leaders in lithium production. This is a global lithium map that contains all the resources of lithium. We can see in blue the lithium from continental brines. We can see a high dense in the lithium triangle. In violet, we can see those reservoirs of geothermal and lithium brines here in the US, in New Zealand, in South America, and in Europe. And also we can see in red the lithium deposits from pegmatites and granites. We can see the same map, but this map is only of lithium from salt flats or brine deposits. We see the high dense in South America. And also in the right, we can see the lithium triangle in Bolivia, Argentina, and Chile. This triangle today is extending to the south of South America and also extending to the Paraguayan basin. Regarding the deposit models, typically we can find two models, the Bradley and the Houston one. Bradley, here in the top left, presented a model with that explains the potential sources of lithium in brines, the pathways, and also the mechanisms of removing lithium from brine pool and concentrations. And they studied a lot of salt flats around the world, and they found common elements in those salt flats. Typically, in all these reservoirs, we find arid climate, close basin containing a salar, tectonically driven subsidence, associated igneous or geothermal activity, suitable lithium source rocks, some aquifers, and sufficient time to concentrate the brine. In the bottom part of the panel, we can see the Houston model, and Houston and his colleagues essentially classify the salt flats in mature, which are halide dominant, and immature, which are clastic dominant. Today we know that we produce lithium from both mature and immature. Immature does not mean that we cannot produce lithium from clastic dominant salt flats. Okay, with the deposit models, we can fit the exploration objectives in geophysics. Essentially, our objectives are similar to hydrocarbon. We want to find, a structural characterization and fluid detection. So our objectives will be the characterization of the salt flat in depth and basement delineation, detect the main structures and main faults, fluid detection, and also the detection of semi-fresh water aquifers that contribute to the recharge system and are very important to study the balance of these hydrogeological systems. Well, let's move to the analysis of different geophysical responses in salt flats. First of all, I want to highlight for those who are not very familiar, are not geophysicists, that in geophysics we have 4 big groups. In geophysical prospecting: seismic, electric and electromagnetics, gravity, and magnetics. And since 2018, with our group, we were studying different geophysical methods different responses in different cell flats. And we justify the reasons for discarding some methods or some reasons to work with some other methods. We have studied different responses in these cell flats in the northern part of Argentina. And let me tell you very briefly why we discard some technologies. For example, in magnetics, we discarded magnetics because in general, I mean, magnetics is the same problems as hydrocarbons or any. Typically, we want to find a magnetic basement covered by non-magnetic sediments. But in lithium, happens that sometimes the basement is an hydrogeological basement with a weak magnetic response. Also, magnetic is not easily cannot be easily integrated with magnetotellurics and other methods, and it's very difficult to find susceptibility data from wells. So if we move to seismic, reflection seismic or refraction seismic, we conclude that reflection seismic, and we have very low impedances contrast, reflection seismic could be good for basement definition and for finding main faults, but the logistics is very complicated, and the added value of reflection seismic is not superior to the added value that has other methods like magnetotellurics and gravity, who can also characterize the basement. Regarding refraction seismic, and given, of course, certain characteristics of the devices and equipment, we find that we have a lot of high velocities halides, so the method can have serious problems. And in all the sections that we have analyzed, we observe that we never reach the ordovicic basement. So we discarded this technology. Then gravity is a very good method to contribute to the structural characterization and basement delineation. So we will use gravity in lithium prospecting. Regarding electrics and electromagnetics, the electromagnetics and electric methods are very promising in lithium prospecting, but some methodology with certain equipment that works very well in conventional mining and water prospecting are not efficient in lithium prospecting due to the low electrical resistivities that we have. Typically, we have electrical resistivities of 0.1 ohm meters to 0.5 ohm meters, very, very low. So some method that works very well in water prospecting or conventional mining in lithium are not efficient in terms of deep structural characterization and deep fluid detection. Well, we can find the two groups, direct current and electromagnetics. Direct current, essentially, the physics is governed by the Ohm's law, whereas electromagnetics, the physics is governed by the Ampere and Faraday law. In electromagnetics, we have a primary source that induces a signal in the conductive layers saturated with brine, which in turn induces a secondary electromagnetic field, and we collect the electromagnetic signal in surface. In direct current, we have the conductive layer saturated with brine, and the risk is that the highest density of current flows through this high conductive layer. So the investigation in depth is very complicated. We cannot pass the conductive layer. So this is a chart or a table that classifies and shows the different nomenclatures of the different methods in direct current and electromagnetic with artificial source and natural source and hybrid source. Essentially, in blue, I highlighted those methods that are used in lithium prospecting in South America. And in red, here I show the discarded technologies: vertical electric sounding, time domain electromagnetics, control source audio magnetotellurics, and scalar control source audio magnetotellurics. And in green, I show the multiphysics toolkit that fit the exploration objectives: electrical resistivity tomography, magnetotellurics, and gravity. So let me now show some examples that explain why we discard some technologies. For example, here we can see a section in the Pozuelo Salt Flat with 2 stations. We collected vertical electric sounding, and then we model and we found that the method do not pass 10 to 15 meters depth. Typically here we used a Schlumberger device with 600 voltage and an AB of 2000 meters. So vertical electric sounding is not efficient in terms of deep exploration, of course. The same happens with time domain electromagnetics, typically with equipment that uses 30 amperes and 2.5 and 25 hertz of frequency, and also loops of 200 per 200, we find that the exploration inside the salt flat, let's see the location of this A station and B station, we see that both the model data and the field data shows that we don't pass 100 meters depth. Also, we see that time domain electromagnetics is a 1D method. Sometimes we see that there are some 2D profiles which are interpolation of 1D models. So we have to be careful with this, with the dimensionality of time domain. The same happens with the vertical electric sounding. Regarding control source audio magnetotellurics, we have, again, the same problem. The control source audio magnetotellurics, and I still don't understand why people still use these systems. Typically, this method is an hybrid method. This means that we have a source of 1 kilohertz and frequencies and higher frequencies combined with an audio magnetotelluric signal. So we are in the audio band, and the strength of the method is in the highest frequencies. So in a salt flat, which has 0.1 ohm meter, we see that the method do not pass 150 meters. And if we see the model data and the field data, we see here we have the electrical resistivity, phase, and coherency. We see low coherencies. Here is an example in Rio Grande salt flat, inside the salt flat. We will see that the model found do not pass more than 120 meters depth. This is because the high frequencies of the control source audio magnetotellurics. Also, remember that control source audio magnetotellurics, I mean the equipment used, do not allow a full tensor exploration, and in general do not have a high storage capacity. Then we have other different methods like scalar control source audio magnetotellurics. The problem in this method is that you can only calculate the Cagnard resistivity or 1D resistivity, which is a very weak hypothesis in lithium prospecting. Today, we know that the majority of the salt flats are 3D problems. Here in this table, this is a summary of the differential physical responses and the characteristics. Here we have the methods and also the properties, I mean the sensitivity to structure, sensitivity to fluid, depth of investigation, field operation, dimensionality, and the main application. If we see the seismic methods, we have refraction seismic and reflection seismic. Refraction can be, as always, we know, good for lithology, but we have a strong risk with high velocity halides. And reflection seismic in lithium can be useful only for basement definition. If we move to electric and electromagnetic methods, we see that full tensor magnetotellurics is the best method in terms of sensitivity of structure and sensitivity to fluid. The exploration is shallow to depth. And also, as it is full tensor, we can find some attributes that provide information of the lateral variation. Also, electrical resistivity tomography is a method that is shallow, but provides a 2D to 3D high resolution sections, and it's very useful to detect the freshwater and brine contacts in the edge of the salt flats. And regarding the potential method, gravity and magnetics, if we have to choose between gravity and magnetics, we will choose gravity because has been proved as a successful tool for structural basement. And also we discard magnetics because we need a magnetic basement, and this is not always happens in lithium prospecting. So here in yellow, I show the effective multiphysics toolkit, and from now I will show the field case and the validation of these three methods. Well, let's move to the examples. Here is the Pozuelo salt flat located in the northern part of Argentina. Here in the top left, we can see the geology of the Pozuelo salt flat. In yellow, we see the quaternary sediments, and in gray, the salt flat itself. And in the right, we can see the Pozuelo salt flat with the survey design. In green, we located the electrical resistivity tomography lines, and in blue, inside the salt flat, we measured gravity and magnetotellurics. The red dots are monitoring wells. This case study is very important not only for the lithium industry, but also for the geoscientists, because in 2018, Lithium Resources, the operator company, acquired 330,000 hectares per $85 million. And after executing the geophysical program, being successful in 10 drilling wells, they constructed the static reservoir model, and they performed the resources and reserves estimation. And the result was that they sold 7% of the initial package in almost $1,000 million. So this is very important, not only for the lithium industry, but also for the geoscientists in this industry. Well, let's move to the case study and the effective multiphysics toolkit. As I told you, we have three legs: full tensor magnetotellurics, electrical resistivity tomography, and gravity that fits the exploration objectives from the deep target to from the shallow target to the deep target. Of course, for the deep target, every time I talk about deep target, I'm talking about 2 kilometers depth. So here we use gravity and full tensor MT, and the shallower target, we use electrical resistivity tomography in the edge of the salt flat. We will use electrical resistivity tomography to study the hydrogeologic balance in this closed basin. So here we have some pictures that shows the electrical resistivity tomography acquisition. And also here I show a typical section of electrical resistivity tomography, which is a DC method, direct current method, but has a difference with vertical seismic profile. The electrical resistivity tomography is a 2D to 3D high resolution measurement. Typically, the electrodes are separated 10 meters. The depth of penetration depth of investigation here is of about 180 meters. And if we see the colors, in red, we have high electrical resistivity values. And in blue or violet, we have very low electrical resistivity values, typically 0.1, 0.5 meters. And if we go, for example, to the section CC, we will see in the northern part of the section, of the CC section, the high resistivity values are coincident with the topography. And in the south part of this section, this means when we enter into the salt flat, we start to see or to detect the layers saturated with brine in blue, because they have very low electrical resistivity values. And also we can detect the contact with layers saturated with fresh water or semi-fresh water. The same happens, for example, in the A section. In the southern part of the section, we see that the electrical resistivity is very high. And once we enter into the salt flat, we start to detect the conductive layer in blue, and we detect the contact of the conductive layer with a mid-resistivity layer that is a layer saturated with semi-fresh water or water with less content of salt. Let's move to magnetotellurics. Magnetotellurics is the rock star in lithium prospecting. Here, I will show some pictures. For those who are not familiar with magnetotellurics, typically we collect 5 components of the electromagnetic field. Electric fields north-south, electric fields east-west, magnetic field north-south, magnetic field east-west, and vertical magnetic field. This is called full tensor MT. And I want to show some pictures with the field acquisition, and also you can appreciate here the variability of the soil. And also this soil, some of them has very strong mechanical instability. This means that the soil can be very ductile and could be very complicated to perform a survey acquisition. Here I show some other pictures. Here we have the coils, the vertical one, the horizontal one, which collect the 3 components of the magnetic fields. The receiver in orange, here we have the receiver, and the electrodes are located in the extremes of the cables. The system that we use is a KMS system that has particular attributes with the dynamic range and preamplifier. That explains also why we can measure these weak signals. So let's see a typical section of magnetotellurics. Here I show northeast to southwest sections. This is 1 line out of 7. And in violet, again, we have very low electrical resistivities. In red, we have higher electrical resistivities. And we can find here, for example, in Pozuelos salt flat, two main conductive units. Each conductive unit can be 1 layer or can be a multi-layer system saturated with brine. In this example, in this section, we have 3 wells, the well 12, the well 6, and the well number 2. And all the wells validates the section, validates the magnetotelluric model. For example, the well number 6 produces brine in all column, and the MT is conductive in all column. The same happened with the well number 12. And also happens the same with the well number 2 that reached a resistivity layer, which is also found by magnetotellurics. If you see, the magnetotellurics pass all the conductive layer with very low electrical resistivity and can characterize the basement. So in this sense, magnetotellurics is a very good tool, or the best tool, to make the characterization from the shallower part to the deepest part of the closed basin. Here in the right, we have the lithological description of the wells. In violet, we highlight the basement. And here in the top, in the bottom right, we see a 1D model I will show again later. I want to also compare, and you can see this in this paper, compare the typical response of magnetotellurics. I compare the Pozuelos response with the Arizaros salt flat response. We see the same thing, conductive units that can have 1 layer or a multi-layer system saturated with brine, and we are able to characterize the basement. If we compare the Pozuelos salt flat with another example, for example, in Saudi Arabia, we can see that the geophysical signature is the same. What I mean, we have a 1D model, this is in Argentina, with electrical resistivity values very low, and this shows a multi-layer system of three layers. And we can see that in Saudi Arabia, this is an MT and CSEM measurements in Saudi Arabia. That shows that, again, the electrical resistivity values and the signatures are very similar to the salt flats in Argentina. So a question here is why MT fit the exploration objectives? And well, the explanation is in the skin depth physics. For those who are not familiar with the skin depth physics, we have this formula, and we can summarize this form, approximate this formula. This is the Bosov approximation. This formula means, well, delta is the skin depth, rho is the resistivity, and F is the frequency. This formula explains the success of MT. This means that the higher electrical values, the higher depth of investigation we will reach, and the higher frequencies, the lower depth of investigations we will reach. So, or the inverse, if we have very low electrical conductivity values, our exploration depth of investigation will be very shallow, and if we have high periods, our depth of investigation will be very deep. So if we take a typical Brine's electrical resistivity of 0.1 ohmmeters, and we apply this formula for different frequencies, we will see that audio magnetotellurics and control source audio magnetotellurics typically is located in this range. And magnetotellurics plus audio magnetotellurics covers all the conductive, covers all the columns, and we can reach deeper and deeper exploration depths. So in conclusion, the very low electrical resistivity values are compensated with very, very low frequencies, operational frequencies. Also, we need to highlight the receiver characteristics, and this is very important because, as I told you, the signal is very weak, so we need a very good storage capacity. And also, there are some other attributes related to the dynamic range and the preamplifier that helps to improve the signal amplitude collected. Well, finally, the third method of the multiphysics toolkit is gravity. I think that all of you are familiar with gravity. And here, typically, again, this is the example in the Pozuelo salt flat. In red, we have the maximums, and in blue, we have the minimums, and the contacts are in the white lines. The point with gravity is as follows. We measure one gravity value, and we have to calculate two variables. We have to calculate the density and determine the depth. So in this sense, gravity has some ambiguity, but as I told you before, gravity is easily integrated with MT, and in this case, we constructed some pseudo wells with some attributions, so we can provide some better resolution to gravity that characterize very well the basement and the main fault. Has a very good response in structural characterization. So if we integrate MT with gravity, and in this case, we did through the construction of pseudo wells, we transform pairs in velocity depth, and then we use density velocity relations, we can provide a better resolution to gravity, to the basement location in depth. Finally, with geophysics, this means electrical resistivity tomography, MT and gravity integrated with MT. We are ready to construct a static reservoir model, and once we are ready to construct once we construct the static reservoir model, we are ready to perform the resources and reserves estimation that in this case were derived to a successful cell. Here we see the static reservoir model of the Pozuelo salt flat. In violet, we see the basement, typically with geophysics and with information of wells and neutron density logs. We found the deepest basement at 900 meters depth. And we assume that the field salt flat has 1.2 grams per cubic centimeters, and the basement has 2.4 grams per cubic centimeters of density. So here we discriminated 8 lithophases, and this is the static reservoir model. So finally, I want to make a very brief introduction to sustainable green lithium that is very important today in Europe and in the US as well. When every time that we talk about sustainable green lithium, we talk about the production part. We don't talk about the exploration. The exploration is the same. So the sustainable green lithium comprises all that process that achieve a lower CO2 footprint, consume less volume of water, use less amount of chemicals or solvents, also leave a smaller physical footprint on land, and reduce the lithium recovery times. So today, the industry and the producers, the operators, essentially are under a green lithium situation if they can, depending on the type of the electrical energy generation that powers the plant, they have to use renewables energy. Also depends on the lithium production method, and also the green lithium depends on battery recycling. If we use this, or we can improve in these three aspects, we will be in a sustainable green lithium situation. So let's move to the lithium production method. Typically, we have the conventional one, and that uses evaporation ponds. Then we have the direct lithium extraction, DLE, and then we have the geothermal, lithium from geothermal, that is the most green situation. So in the conventional one, which is not green, the brines, here in the evaporation ponds, the brines are pumped to the surface into these large ponds, and where the solar evaporation increases the lithium concentration in a period of 18 months to 24 months. So we have the extraction, then they put in the evaporation ponds, and then they have a purification process. All the process takes from 18 to 24 months. Then geothermal essentially is to take advantage of the geothermal plants and obtain lithium from geothermal brines. Typically, we can find, or we can mention in Europe, in Germany, in the Rhine Valley, these geothermal brines, or lithium produced from geothermal brines. Also, the Salton Sea in California, US, and also we have some interesting geothermal points in South America. Regarding direct lithium extraction, this is a typical scheme that shows, well, first of all, we want a green situation, so the grid connections have to be connected to 100% renewable power. We pump brines from the brine aquifer, and we send to the direct lithium extraction plant, and then we process. Typically, the direct lithium extraction and refining technology is related to chemical manipulation. The typical methods are absorption, ion exchange, solvent extraction, electromembrane, and electrochemical. And depending on the country, on the company, we can find different stages today. We have some companies that are in the lab phase, others that are in the pilot phase. other ones that are in the demo and commercial phase. If we want to compare direct lithium extraction with conventional ponds and hard rocks, this means spoduments, we have to see the production times. In the case of the DEL, the production times are from hours to days. In the evaporation ponds, as I told you, from 18 months to 24 months to years. Regarding the land area requirement, the direct lithium extraction has a very low land area requirement, whereas the lithium extraction from evaporation ponds and mining hard rock has a high land area requirement. Regarding water consumption, indirect lithium extraction is very low, whereas in the lithium brine and mining hard rock is high. To have an idea about the water management, typically to produce 1 ton of lithium, we need 3,000 tons of water. So this is a hot issue today. And regarding the lithium recovery rates, which is very important as well, typically the direct lithium extraction recovers from 70 to 95%, whereas the lithium brine extraction in evaporation ponds recovers 40%. The same happens with mining hard rock. We can obtain 6 to 7% of lithium in 80% of spodumene or hard rocks. If we want to compare the lithium hard rock with brines and geothermal in everything related to the CO2 footprint, we see that the ton of CO2, the ratio of ton of CO2 to ton of LCE, which is lithium carbonate equivalent. In hard rock, we have 50 tons of CO2 per ton of lithium carbonate equivalent. In brines, we have 5, and in geothermal, we have 0. So lithium from geothermal is the most green method, production method. Regarding water consumption, the same. We see that the relation decreases drastically in the geothermal production, and the same happens with the land area requirement. Well, as I told you, the sustainable green lithium is related to the production ways, battery recycle way, and today we see that mainly in Europe and the US, there are a lot of companies that are working on research and development or deployment steps, but they are strongly working on different methods of battery recycle. And to have an idea, the recycled materials could contribute between 30 and 60% of battery cell production by 2040. And also, it is estimated that we have a reduction of CO2 production of 72%. So, well, I'm finishing the talk, so I will conclude. Well, during this talk, we have been discussing about the different geophysical responses in different salt flats, finding that full tensor magnetotellurics, electrical resistivity tomography, and gravity comprises an effective multiphysics toolkit in terms of shallow to deep exploration in salt flats. Typically, the exploration depth is of about 2 kilometers to days, and we have also new paradigms, for example, basements fractured and saturated with brine, and anomalous concentrations of brines in clays. Also, we have justified the reason for discarding some geophysical techniques. Of course, physics always works. This depends on the equipment and the offer of the manufacturers. We also reviewed or provide a table that compares the weakness and strengths of these different geophysical methods and the main applications in brines prospecting. And finally, I provided an introduction to sustainable green lithium, showing that the sustainable green lithium are related to production and not to the exploration part. The most green method is the brines produced from geothermal, and direct lithium extraction is also a method that is considered green today. And we need also to have a our plant connected to a renewable energy source. And also we need to consider the recycling of battery to make more green the lithium production. So thank you so much.
Thank you for a very interesting webinar. Discussed quite a lot, quite deeply the different methods and applications, and also the production methods. So very interesting. We can turn to the Q&A. So as a reminder to so the webinar is recorded, and then the recording will be available soon, or we can remind on that. Are there any questions? Let's see, checking the Q&A box. I don't see that questions. Laurie, do you see any questions yourself?
Yes, I see. Looks like Mohammed has his hand up.
Hi, Anna. Yeah, thank you for interesting webinar. And I have a question about the empty section you showed. That would you please explain which method did you use? And as I see, there are the very conductive layer in the show depths. It was very interesting how to solve this in the inversion.
Yes, I'm sorry, but the question, what is how we obtain this inverted model? How we perform the inversion?
Yeah, which method did you use?
For the inversion, typically, no, we use in this section, this inversion in particular was a 2D inversion. From the mathematical point of view, we used non-conjugate linear gradients. And the RMS were quite good, like around 5%, if I remember well. So the point is that the electrical resistivity values are very low. So this helps. Seems that it's complicated, but this helps because the contrast is very high. So the inversion is not very complicated. We don't have a lot of, we have ambiguity, of course, but because it's inversion. But the contrasts are very strong. So the conductors, if you run one model, another, are very well identified. We don't see a lot of artifacts, actually.
It is a joint TE and TM?
If we perform, no, in this case, we made a collaborative inversion, and let me explain why. Because typically a joint inversion use the cross gradients algorithms. For cross gradients, you have to assume that you have a parallelism between MT and gravity. And this is not always the case. Essentially, you don't need a similar structure to find a similar structure with gravity and MT. Because you, as I told you, you can have, for example, some cases where the basement is saturated with brine. So what is, you see the basement with gravity, but the shape with MT is completely different. So we need to be a little bit careful when we use cross gradients algorithms. So in this case, we made this collaborative integration between gravity and MT through the construction of the pseudo wells. Of course, this is the most sensitive part of the study, but we were successful in the prediction of the depths of the new wells. So I think that we are okay with these assumptions.
Okay. Which range of the frequency did you use?
Here, typically, we use from 0.001 hertz to 50 hertz in practice. Our data is collected from 0.001 hertz to 70,000 hertz, but we took the range up to 50 hertz typically.
Okay, thank you, Anna.
Oh, thanks to you.
Thank you, Mohammed. The next question. So I see there's many questions, several questions in the Q&A box, and we'll come to that. And first, what was the process? It's from Erin Ernst. What was the process to go from the geophysics to the static reservoir model?
You mean what was the process? Well, in general, the workflow is very similar to hydrocarbons. Let me know if I'm answering what you want to know. But in general, the process is very similar to the hydrocarbon industry. We obtain geophysics. In a way, we want to determine to characterize the basement and to determine the depths and the deepest basement. And once we have the geophysical model and knowing and discriminating the different units, we integrate geophysics with the wells using logs information, lithology, and in this case, we could discriminate 8 lithophases. And in this way, we constructed the static model using other software, not the geophysical software. In this case, we use the Sequent platform, and we obtain the static model that provides all the topography of the basement, and this information is used to estimate to perform the resources and reserves estimation. I'm not sure if that was the question.
I don't see if Erin, if you would like to answer the question yourself, please raise your hand and we'll unmute that. But I think your answer is perfectly describing if I am. Oh, there is Erin. Please, let me see.
Can everyone hear me?
Yes.
Yes.
Okay. Yes. Hey, thank you. Thanks a lot for the presentation. It was really, really good. My background is mainly in seismics, so I'll have to ask you something about that. You said in the presentation that the logistics is not that easy for this kind of project. And the question is, I saw that you only used, like, in the project 48 channels, so maybe it's a problem of technology. Maybe more channels and stuff like this would have been better, and maybe would have shown a better image of the structure underneath the salt.
Yeah, yes, you are absolutely right. We are not discussing about physics. We are discussing or putting into the table the equipment limitations maybe in the market. And of course, in the case of refraction seismic, we need more offset and stronger sources. But as I told you, we have a lot of issues. If we want to use explosives, it will be very difficult here. If we want higher sources with more weight, we have a lot of mechanical instability in the soil. This means that we have the soil, and after 10 centimeters, you find water sometimes, so it's very difficult. And regarding reflection seismic, of course, there is a strong cost, and that is the main problem. And typically, the seismic that was collected has a mid to deep objective, not a shallower one. And that was because of the high cost that seismic has. So this resulted that reflection seismic was only used for basement delineation and for detection of main faults. Also, those layers that are absolutely saturated, because you have multi-layer systems, but it's all saturated with brine. The brine goes everywhere. It moves and goes to everywhere. So This results in low acoustic impedances, contrast, and maybe the added value that can have seismic in these problems don't have a strong added value. But of course, physics works and always is equipment or market offer limitation.
Okay, thank you.
Thanks, Mihai. Thanks. Edin, would you like to ask your question and check on the answer?
Sure, yeah, thank you. Can you hear me, Anna?
Yes.
Yes,
yeah,
hello.
Awesome. Hello. I mean, you mostly answered it already. I'm just curious, you have the geophysical properties, you had a little bit of borehole information, but not a lot. So how did you build those relationships between the geophysics and the intrusive information? Did you use statistics, or how was that done?
Yeah, this is the most sensitive part of the study, I confess. Yes, we don't have a lot of information from wells. If we are lucky in some salt flats, we can have some resistivity, SP and gamma value from loggings, but it's difficult to have density values. So we have to make a lot of assumptions and recalibrate. Finally, we found the way of connecting electrical resistivity with density, but again, it's the most sensitive part of the study, and we have to be careful with this. The construction of the pseudo wells is very common in the gravity during the gravity interpretation.
No, that's great. Thank you.
No, thanks to you.
Thank you. We have another question in the Q&A box, and that is, what about, that's from Dan Hollis. If you'd like to ask yourself, please unmute and ask. What about using ambient noise seismic tomography for mapping the basement?
Yeah, yes, good question. By the moment, we didn't try this this application. So this could be a good, this is a good advice to try to make a field test and see what happened. Yes.
This is coming from interferometric measurements, or is it coming from?
Yeah, hi, this is Dan Hollis. Great talk, Anna. Yeah, so yeah, it's through interferometry, and you know, it's very good at mapping basement and like that. It may, I guess one of the question is a little further question is, you know, in the reflection side, do you see any you know, reflections out there that give you an idea of structure that somehow relates to brine concentration?
Yes, we see an idea of the structure, but not that we used to do in hydrocarbons, layer by layer, and to run attributes. We see that it's not enough for that purpose. But yes, with reflection seismic, we can make a structural characterization. Yes.
All right. Thank you.
Thank you, Dan. Thank you. I guess there was a question from Jaap Mons. Is there a way of determining the lithium concentration in brines directly?
This is a typical question. No, we measure. I mean, we don't. To be honest, every time we said lithium exploration, we have to say brines prospecting or brines exploration. And the brine can contain lithium, magnesium, and other minerals or salts. So it's not a direct indicator of ppm, of lithium ppm, but if we have very, very low electrical resistivities, like 0.1, this situation most likely will be brine than, for example, we can have brine or we can have wet clay. If we have very low electrical resistivities, most likely we will have brine. But the answer is no, we cannot. in geophysics, with this geophysics, we cannot determine the ppm of lithium.
Thank you. Jaap, if you would like to answer for the questions, please unmute yourself. And we have one more question in the Q&A box. Says, is geophysical data from the case studies available for practicing?
No.
Published? Yeah.
No, it's not. No, because the owner is the operator company, so no, it's not available. Again, in the paper, there is an interpretation paper that you can download, and there says that no, we don't provide the data because the owner is the operator company. But I hope one day to share the data.
And maybe then another question, that maybe more challenging question in the chat box. It's a challenge to, of course, to extract 1 ton of lithium and require 3,000 tons of water. So, if applying any hydrogeology modeling, what's the source of the water? That's, I guess, the question is.
No, I didn't get the question very clear.
In NGT, what is the source of the water to be used for?
Well, during the exploration, we explore brines aquifers, but also we explore freshwater aquifers. We do the both exploration, and with electrical resistivity tomography collected in the edge of the salt flat, we determine or we study the charge discharge system. So we made simultaneously both explorations of brine aquifers and freshwater aquifers.
Yeah. So then we have information about both systems, and we can use that information further. Thank you, Anna.
No,
and there was another question on the cost of among methods, and I think you had it on one of your slides, and then perhaps it's the direct was the second costly, and then.
You mean cost, like economical cost, or
yes, economical cost?
Okay. Well, typically, of course, the cost depends on because these areas are very remote and are located at high altitudes, and there are other areas that are easier. But in general, the cost is similar to hydrocarbons. If reflection seismic cost 10. MT can cost 3 and gravity can cost 1. That is the relation.
Thank you. Are there any regulations, like for hydrocarbons, there is regulations on the areas for exploration? How is this regulated by the government?
Regulation? Yes, in general, at least in Argentina, the regulations are under the mining laws or mining regulations. And also there are some secretary of hydric resources that make some controls in the water management and in this type of productions.
Yeah, so keep that under control. Thank you, Anna. I think that's probably all our questions. If there are no other questions, then we'd like to say thank you to Anna for a great presentation webinar. And also
thank you so much.
Thank you. And also thank you to SCG for organizing this webinar, SCG Europe Regional Advisory Committee.
Yes, thanks to the European Advisory Committee and all the organization.